Now let's begin. So last day, the first day, that means yesterday, we actually discussed about telescopes. I'm not going to discuss it anyway, one more. But I will just skim through the slides just to show you. We spoke about there are different kind of lights which we cannot see. We can see only the visible light. So there are telescope in other kind of lights as well. So we haven't discussed that yesterday, but we will be discussing that today. And these are all some examples of telescopes and why we have telescope, and we compared it with eye, and a funnel and a telescope can be made a good analogy together. And we said that there are telescopes that is actually made using lenses, and there are telescope which is made using mirrors, and Newtonian telescope, then Cassegrain telescope, and why we need big telescope to make high resolving power, and what are different kind of mounts, altitude azimuth mount, azimuth mount, equatorial mounts. Then some major observatories, just a few, maybe only selected ones: CX Observatory, Large Grand Canyon, Keck Observatory, International Liquid Mirror Telescope, and an overview of an infographic on how large those mirrors are when compared to the size of human being, or how they are compared in between. So that is where we stopped yesterday, if I remember correctly. Okay. So now today we will be continuing with the remaining session. Just a second. Remaining topics. So first of all, let me start with this diagram. Okay, here imagine that this is something, an interesting graph. This is, I will try to explain. So here, see that, just remove this, just avoid all these things like this, telescopes and all. So here you can see, as we discussed yesterday, this rainbow of colors is actually representing the visible light. Okay, this is visible light, and to the left and to the right, okay, of the visible light, actually we have different types of lights, as we discussed yesterday. So ultraviolet is there, X-ray is there, gamma rays are there to the left of this visible light, and to the right of this visible light we have infrared, microwave, then radio waves are. Okay, so now why this graph is something looking weird, something like some ups and downs and opening. So you can imagine, like, when this line, or this brown region, we call it as a, it's not a proper brown anyway, but assume that this is a high. Okay, and when it is high, that means that atmosphere doesn't allow, it is actually blocking these waves. So when it is high means, if gamma rays are coming from here, the gamma rays will be blocked by the atmosphere. Here you can see X-rays, ultraviolet. So up to ultraviolet, almost all of the lights are being blocked by. So from gamma rays to ultraviolet, those lights are being blocked by atmosphere. Now you can see a gap here. Okay, so see a gap here. What is the meaning of that gap? That means the atmosphere is allowing the passage of this light. And after that, that the meaning is, whenever this is a high peak or high like this, that means that kind of light will be blocked. Okay, whenever it is shallow, something like this or like this, that means that type of light is allowed by that. So here, which are the most allowed? Actually, you can see that the visible light is allowed, and many of the radio lights are also allowed by the atmosphere. So the radio is allowed and the visible is allowed. And here you can see this is red. Beyond red, there is some infrared is there. So some amount of infrared is also allowed. Okay, and some amount of here, some microwave is there, or maybe microwave comes here. Anyway, some part of the infrared is allowed, but most of the infrared is actually blocked. Okay, so what is the takeaway from this? Yeah, gamma ray, X-ray, ultraviolet, write it as UV, and most infrared, okay, blocked by the atmosphere. Blocked by atmosphere. Okay. Then visible light. Okay. Then some infrared, that is IR. Then most radio is allowed by Earth. So that is how it is. Okay. So actually atmosphere, this is a bad thing for astronomy regarding that. The problem why, if you want to observe something in X-ray, or if you want to make an X-ray telescope, you can make one. But if you make one at Earth's surface, if you try to place it on your terrace or maybe at some very good location on Earth, you won't get X-ray. Why? Because the atmosphere is not allowing the passage of X-ray. So atmosphere will be blocking the X-ray. So you won't get any X-ray at the surface of Earth. So if you make an X-ray telescope at the surface of Earth, you cannot see anything with that telescope. So it is a, we can say that it is a useless telescope if you place it on the surface of Earth. So if you want to make an ultraviolet telescope, that is the same. And most of the infrared, the same thing. Okay. So one thing we can do, observe in the safely, we can observe on Earth's surface is visible light and most of the radio actually. So other than that, all other kind of lights are mostly blocked by Earth's atmosphere. So that is a big issue. But this issue is only an issue for astronomers. Otherwise, it is actually a boon for us in the sense that if the gamma rays or X-rays or ultraviolet, if it reached the Earth's surface completely, then this life, this kind of the life that what we are seeing right now won't be possible on the Earth's surface, because they are all high energy rays. You already know that even experiencing high energy rays for a long period of time is not good for human beings or life forms, not just for human beings, for any planet or plants on the surface of Earth. So X-rays are okay because we are having X-ray for a very short period of time, and it is not that hard X-ray or it is not that strong X-ray. That is why when you go to X-ray and you can take it, but if you are exposed for X-ray for a long time, then it is actually not good. Even the ultraviolet or gamma ray, the same thing. So atmosphere actually protecting us from this harmful radiation, but that is a problem for astronomers in the sense that we cannot observe it from Earth's surface. But there is no point in thinking it is a problem for astronomers. If the life is not formed here, then there is no astronomers at all. Okay, so that's about it. Okay, so this is the main reason why we have to send telescope to space. Okay, for visible light, there are many other advantages as well that I will discuss later. But if you want to make gamma ray telescope or X-ray telescope or an UV telescope, or you make an James Webb Space Telescope, an infrared telescope, you cannot keep it on the surface of Earth and observe whatever object that you need. You have to send this to space, then only you can observe the things. Okay, so that is one of the main reason we need to send telescope to space. Okay, there are other reasons, couple of reasons as well that I will discuss when we discuss about the space telescope. So that's it. Now the question is, okay, so these are the things that is coming from there. So I will discuss about the X-ray telescope. So whenever I mention about X-ray telescope, usually we call it as X-ray telescope, but the X-ray, the high energy part of X-ray is actually gamma rays. So most of the X-ray telescopes has the ability to detect gamma rays as well. So the technology is almost the same for whether it is X-ray or whether it is gamma ray. Both can be discussed in the, detected in the same way. Okay, so that is not an issue here. Okay. So that's why most of the X-ray telescope also detects gamma rays, because the technology is almost the same. So let us discuss about X-ray telescope. Okay. So X-ray telescopes. So X-ray telescope, or usually we call it in short as XRT, is a telescope that is designed to observe remote objects in the X-ray spectrum. X-ray spectrum means X-ray light. So we can call it as X-ray light. Okay. So usually, and the problem is that X-rays are absorbed by Earth's atmosphere. So instruments to detect X-ray must be taken to high altitude, either by balloons or by sounding rocket or by satellites. The balloon is actually possible to use sounding rockets. Okay, sounding rocket, if you know that, they are some tiny rockets, not that big as usual launch vehicles. They are small rockets which can be sent to launch to go above the atmosphere, so that from there as well we can observe in X-ray. But the problem is that we can, whether it is a balloon or a sounding rocket, it won't stay there for a long time, and we cannot actually properly orient in whatever direction you need. So that is a problem actually. So satellites are the best option for X-ray telescopes actually. And the problem with another issue is that, and this is an example of Chandra X-ray Observatory launched by NASA in 1999. You see, this is launched in 1999. Okay, and for sure it is even before the birth of you. Okay, a few years before before your birthday, and you can see this is still operational. Okay, it is more than 24 to 25 years actually. So now the problem with the usual, there is a huge difference between the usual telescopes that we have seen yesterday and to the X-ray telescope. So for a usual telescope, we know that there will be a mirror. Okay, I'm just not going to discuss about lens here because the lens is not used in big telescopes nowadays. And we have a mirror. The light can come here, and light will be focused to some point, something like this. If you remember yesterday's diagram and all, this is the way. Okay. Now I am taking such a mirror, and let us focus the same light using X-ray or for X-ray. So some X-ray is coming in this direction. I'm using a telescope here to focus that light. The problem is that for almost many of this thing, the thing will happen. The X-ray won't get reflected with the usual mirror. It will just go in through that. Okay, it will pass through that like this. Okay, so it won't stay there, or it won't be reflected there if you use a usual mirror. Okay, either it will be passed through or it get absorbed by the material of the lens. Okay, it will be absorbed. So for a telescope, it has to be either reflected back, and if it is a lens, it has to be deflected to a point. So how can we make X-rays to reflect or deflect to a certain point? Okay, so that is the issue that is there for X-ray telescope. So we want to focus X-rays to a point like a lens, or in other words, we can say that X-ray need a kind of a lens. Okay, so that kind of a lens is what you're seeing here. Okay, so this is, we can call it as an X-ray lens. Okay, you can call it an X-ray lens. Okay, or usually we call it as another name. Simply we can call it as X-ray lens, or it is called the grazing incidence mirrors. Okay, so what do you mean by grazing incidence mirrors? Okay, let me explain it. Before going to the diagram, I will explain it another way. Okay, so just imagine an X-ray is coming in this direction. So it is in straight line. Okay, assume that X-ray is coming in straight line. So if I place something like this, then what will happen? Either that X-ray will be absorbed by the material, or it will just go through. This is the two options that it has. Now, instead of that, I use some kind of specific metal or something like this, and I place a mirror. It is basically a metal. Even if we call it as a mirror, it is not a usual mirror. It's a type of metal, and I place it not exactly perpendicular, at a slanting angle, at a grazing incidence. Okay, so that when it comes and hit it, okay, so you can see that it is hitting it not directly, something like a head-on collision. It is just simply touching on this edge, and it will be slightly deflected. Okay, so the problem is that if I place it something like this, then it will be absorbed. So that I have to make it slightly tilted. Okay, not too much. Okay, so it has some mathematics and all, how to keep it up, all those things depending on the material that you are using. So there is science behind that, not that simple. Anyway, so that it will come and hit, it will be deflected. Now I place one more here. Okay, if I place one more here, what will happen? Again, one more deflection will happen. Okay, finally it can be focused to a point. So here you can see that the first red light is coming. Okay, that is X-ray, and here a small deflection, another deflection, and it reached here. Then I place one more here. Okay, So it is not just a plane, it is actually kind of a circle. Okay, you can see the shape is actually parabolic shape or hyperbolic mirrors. So some kind of a circular or some oval shape, there will be a lot of them. You can see it is an array. So here if you zoom into this picture, you can see that this is not a single sheet. Here there are many actually, tiny you can see, and those things can actually deflect the X-ray to come to this point. Okay, so it is everywhere, and even from this direction it is coming, from here it is coming, from here it is coming. So finally it can act like a lens for X-ray telescope. So that is why it looks some kind of different. Okay, here you can see that here also what you are seeing is actually the deflector. See, in Chandra X-ray telescope. So that is one method of getting the X-ray focused. Okay. Okay, so that is happening here. Now let's see, another method is there that is called collimated apertures. Okay, so collimated apertures is actually there are many kind of aperture method is there. So one interesting method is that there will be a mask. Okay, so see, I am taking a some lead block or something which doesn't a thick metal block, so that doesn't allow the passage of X-ray, and I put some purposeful holes there like a mask. I will put some hole in a specific pattern. Okay, I put some pattern, so that is what you are seeing here. See, this is a mask and this is some open places inside that. Okay, now if I have a beam of X-ray here and another beam of X-ray is here, and that two beams will cast a kind of a pattern. So just imagine that this is very simple thing. Take a paper and put some pattern of holes like this, and now shine a torch from this direction. It will make a pattern here for sure, not exact almost the shape of this, but anyway it will make a pattern here, and you can see that there will be a shadow depending on at what distance you are shining the light and what direction it is. Now your friend is also shining another torch from this direction, and here there will be another pattern. The same pattern will be copied here, but in a slightly different way. So even though the patterns are same, there will be some difference in between because of the direction in which the light is coming. Okay, so it will make a pattern on the below paper. So from this paper, from this pattern, if you know this mask, what was your mask and what is the pattern, actually you can determine what is the X-ray source is, or what kind of source, what is the shape of the source. Okay, so the shape of that source of light can be determined by just analyzing the shadow. So that is something called a coded mask, and based on this, using some computer mechanism and some mathematics, actually we can find out what is the source looks like. So that is here. Okay, and for this beams to come, there will be some other techniques will be also used. So this is another way to determine what kind of source it is in X-ray telescopes. So that is about X-ray telescopes. So X-ray telescopes are unique in the sense that even if I see this kind of one for the first time, if you see something like this, we won't even feel that it is a part of a telescope. So it looks like something else. But this is one of the ways in which we can actually focus X-ray, because X-rays are usually won't get reflected by a mirror. Okay, and that's it. Now, another best example, one of the most famous X-ray observatory is the Chandra X-ray Observatory. Here you can see. So that is about, it actually launched in July 23, 1999. And the mission duration is already 24 years. I think, yeah, the coming July it becomes 25 years actually. The diameter of the mirror. So even though it is not a proper mirror, okay, we cannot call it, when we hear it is a mirror, but it is a kind of a mirror. But anyway, the size of this thing, that lens or that mirror is actually 1.2 meter in diameter. Okay. And it can detect X-ray in a specific wavelength. Actually, this is a wavelength in which it is observing. Just leave the wavelength anyway. So it is actually launched in 1999 in the Columbia Space Shuttle. And Chandra is sensitive to X-ray sources 100 times fainter than any previous X-ray telescope. So it is one of the, and it is actually, that if you know, you just note this as well. So Chandra is one of the great observatories. That means NASA actually sends some important telescopes. They are together called the great observatories. Okay, and one of them is actually Hubble, and that is one of the great observatories. Then Compton Gamma Ray Observatory. Then another one is Spitzer Space Telescope. So these three along with the Chandra X-ray Observatory. So these four of them together called great observatories by NASA. Okay. And it is actually a satellite. Okay. Anyway, if you know that this is a space telescope, so why it is a space telescope? Yeah, we cannot observe X-ray from the surface of Earth. So it has to orbit at a height. So it is orbiting around Earth. It is simply a satellite. Okay, so it is orbiting. We can orient to whatever direction it needed. So it is a 64-hour orbit. That means it takes 64 hours to complete one circle around Earth. Okay. Mission is ongoing as of 2025. Then the telescope is named after the Nobel Prize winning Indian American astrophysicist Subramanian Chandrasekhar. So if you came to read about especially stars and all, you remember the Chandrasekhar limit. It is actually came after his name, that is the Subramanian Chandrasekhar. So then it is named after him actually. Okay. And there is one more interesting. It is actually previously known as, the first name of the telescope was not Chandra X-ray Observatory. It is actually Advanced X-ray Astrophysics Facility, or XAF. That was the initial name. Then later it named to Chandra X-ray Observatory. Now another one, X-ray Multi-Mirror Mission Newton, or XMM Newton. It is usually called XMM Newton. So it is another interesting kind of telescope because it has three telescopes actually. It's not just a single X-ray telescope. It has a three telescope. Okay, launched by European Space Agency. The other was by NASA. This is by ESA, European Space Agency, December 10, 1999. It is also in the same year as that of the one. And this mission is also going on. It is still working. That is 24 years. And the mirror diameter is 70, and the outer mirror is 70, and inner mirror is 30. So what you mean by outer and inner? So if you know the structure, you can see that two set of mirrors are there. This is the outer mirror. This is the inner mirror. Okay, so that is what's specified. Okay, then named after, you know that, Sir Isaac Newton. Then tasked with investigating interstellar X-ray sources. Okay, then ESA. And there is one more interesting thing regarding this telescope is that along with an X-ray telescope, it also has an optical telescope as well. Okay, so this is for an X-ray telescope. That is why it is called an X-ray multi-mirror mission Newton. So multi-mirror because it consists of different mirrors. You can see that is three folds. Along with this, there is a small telescope, small optical telescope. Optical telescope means it can observe in visible and ultraviolet. So there is another telescope along with this. Another instrument is there. So that is another telescope, another usual telescope we can call it as. And so the advantage is that whenever it is observing, suppose that there is a source, a galaxy is there. We are observing a galaxy which is emitting X-ray. At the same time, we can actually record its image in visible and ultraviolet. So that is an added advantage for this X-ray multi-mirror mission Newton, or XMM Newton. So ESA is actually plans to succeed another new one, that is XMM Newton, with an advanced telescope, with a new telescope after its lifetime. Another telescope will be launched. ESA is actually planning for that. That is Advanced Telescope for High Energy Astrophysics. So this is one thing I would like to explain right now. So this is something called a high energy astrophysics. That it looks a fancy name. High energy astrophysics means the astrophysics that dealing with a high energy. High energy means, if you remember yesterday, that is we started with the gamma, X-ray, ultraviolet, the order, if you remember, ultraviolet, then what is called the visible, then infrared. Okay, so the left side is actually gamma, X-ray. These are all highly energetic when compared with the others. This is the most energetic phenomenon. So studying the universe, or maybe astrophysical sources using X-ray and gamma ray, is actually comes under a specific branch of astrophysics called high energy astrophysics. So that is why it is called this name. So high energy astrophysics means it usually studies the gamma and X-ray. Okay, and that's about it. Okay, so it is to be launched in 2030. Now let's go and discuss this is the highly energetic telescope, in the sense that this is high energy astrophysics. Now let's go for some low energy thing, that because when you consider this order, the least energetic waves are actually the radio waves. Okay, so radio waves are basically what you are seeing here. It is something like a dish antenna. Okay, so it's basically a dish antenna. But this is not just the only type of antennas actually we have. There are many kind of radio telescopes are there. Something just look like some wire, just some mesh of wires will be there, or maybe something like this. But most of them looks like this. Okay, but there are some other designs as well. But most of the radio telescopes looks like something like this structure, something like a dish antenna. So you can see that even it is transparent. Actually, you can see the other side. Okay, but there is an interesting thing. The radio waves, even without that, okay, even if it is transparent, but there is wire meshes are there. Okay, there will be some crisscross. So if you go and see, I don't know whether you have experience with the proper dish antenna closely. Something we had when I was a kid, there were for TV reception and all. Nowadays there is no need. It is even coming through internet, so we are not using that kind of dish anymore. But anyway, for those dishes, if you see that there will be tiny holes in this, it will be something like a net. Okay, it's not a something like a close woven net. Okay, but this gap is actually visible. We can even put one finger in through that, so it is not that small actually. So it is something, that is why we can see the other side. Okay, so specialty is that, but even though this is transparent to light, okay, so if moon is shining here, the moonlight will actually pass through this, but the radio waves, those are so big waves. Okay, so those waves will be reflected by this dish. So it looks like this. It is also something like a similar telescope. Okay, a mirror telescope. The radio waves will come in this direction. Okay, then it will be reflected to the center portion. Okay, so radio waves are coming, reflected back and reflected back. Okay, so now here at this point there will be something for receiving it. So this is the same structure that of a telescope actually. Most of the telescope also has some camera maybe here. So here there is a receiver here. So this is called the receiver. Okay, so received. So this is the receiver unit, and this is the dish. Okay, this is the dish. So the dish can reflect the radio waves to this center point, and where it will be received and transmitted to, or maybe some using some wires and all, it will be transmitted to the control center of the telescope, where it is being analyzed. And this giant dish can actually orient in whatever direction you need. Okay, so it is actually movable as well. So radio telescopes are special instrument used to detect and study radio waves emitted by celestial objects. A radio telescope works by collecting radio waves using a large parabolic dish on an array of small dishes. Okay, so either it can be a single large parabolic dish, something like this, a big dish maybe, or sometimes we use something called an array of them. A number of them will be arranged in a pattern and it can be used. Okay. Now the collected waves are focused onto a receiver, and which converts them into electrical signals. Okay, and it amplifies, boosts the signals and making them suitable for analysis and is sophisticated. Okay, then this will be analyzed for what object it is and to study the properties of that object and all. So that is basically about the radio telescopes. Okay, see some, I forgot to add an interesting image, but I will show you at the end. Okay. If I forget, just make me remember. I forgot to add that in this slide. So broadly, we can call radio telescope as two types. One is, as I mentioned, it is a single dish telescope. Okay, so use a single large dish to collect and focus radio waves. So one best example is actually Arecibo Observatory. If you have seen some James Bond movie, I think in Die Another Day or something, this Arecibo Observatory is shown there in that in a movie scene. Some action scene is actually happening inside that telescope dish and all. It's interesting. I will show you some pictures later. Then another one is actually array telescope. It comprises of multiple smaller dishes arranged in a grid. Here you can see this is actually the very large array or VLA. Okay, so here you can see this one. Instead of placing a big one, they are actually trying to place smaller and smaller one. So what is the purpose of this? Instead of having a big one, they are trying to make smaller and smaller one. So there comes an interesting technology called the radio interferometer. Just leave the word meaning or the science behind it, because interference even you haven't learned in your class actually. So just leave. Anyway, just understand that radio interferometry is a technique where instead of placing a small telescope, a big telescope, so suppose I want to make a big telescope, something like this, a radio telescope. Instead of this, what I do is that I place one telescope, one small here, one small here, one small here, one here, one here, one here, one here, almost the same size of this. Okay, you can see that if I draw the boundary, a virtual boundary, it's not a real boundary, there is no real telescope there. This is okay, it is almost the size of this. Okay, so instead of making a big dish, something like this, okay, I can make tiny dishes like this. Okay, see. Now, using a technique called the radio interferometry, okay, we can actually get the signals. Okay, so imagine that here the control center, okay, or a control center is here. I can get signal from each of them. Okay, see, each of them. Okay, each of them, and I can combine them together using some technique and actually use it as an entire telescope. So effectively what will happen, this single telescope can act as an entire telescope like this. Okay, so that technique is actually called very long baseline interferometry or VLBI. Just understand that there are this kind of telescope. Instead of making a big dish, we can actually make small one. So if you remember an image of a black hole being captured some years back, I think in 2019 or 18, I forgot actually, something, it looks like a donut. Okay, something, it looks like a donut. That image is actually captured by radio telescope. It is not by using Hubble or any other optical telescope or X-ray telescope. It is actually captured by a radio telescope. And for that, actually, they need a huge telescope. Okay, huge telescope means even this VLA is not enough. Okay, so what they did that, imagine this is our Earth. Okay, and they took telescopes from here, and many part of the world there are telescopes. As you know, here there are telescopes, and many part of the world there are what is called radio telescopes are there. So at the same time, they all simultaneously took the picture of the what is called the black hole. So they simultaneously tried to take the picture and all those data combined together. And it is very interesting that it consists of GBs of data, hard disk, many multiple number of hard disk of data, and all this data actually came to the common center by flight and all. Then they actually combined it together, and we got the picture that we are seeing usually, that the picture of the black hole. Okay, anyway, it is not the exact picture of the black hole. It is actually the outer ring, something like the accretion disk is what you are seeing. Okay, just leave it. Anyway, we got the picture of the black hole using radio interferometry, effectively making a big telescope that is as big as that of Earth. How it is possible? Yeah, even though we have only small telescopes, we can make them able to take a picture at the same time, then effectively we can make it as a big telescope, big radio telescope, and which is that process is known as very long baseline interferometry. So that is a technique they have used. Okay. Now some big. So this is one of the biggest, I think. Okay, this is a 500 meter. See, it is half a kilometer. Okay, half a kilometer size dish. Here, this dish is actually made actually in a natural. Okay, it's in a pink tank. It's in China, so it is actually in a natural basin in between some mountains. You can see Arecibo is also the same, something like the same, and they made a giant dish. You can see. So somewhere over here, okay, somewhere I think somewhere over here there is that suspended small receiver is there. That receiver will collect all the light. So radio waves are coming. So even while we are speaking, the radio waves from all these objects are actually receiving here, and it will be reflected, 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 and we can actually receive them. So this is a big one in China. Okay, it is Tianyan, its nickname, and see it is working till from 2016. The diameter is actually 500 meter. That means half a kilometer. And this is actually not working right now. It is actually got some issue with it is decommissioned actually. It's an old one. So the first light you can see that it is in 1963. This is what is actually featured. It is actually there in the it's actually collapsed in 2020. So even before that, actually it's shown in a film. Okay, let's see that. It's actually so small when compared with the size is actually just 305 meter. Okay, anyway, it is not that small. It is 300 meter, but when compared with this one, it is small. That's all. It's not that tiny anyway. So that is called the Arecibo radio telescope. Now this is what I mentioned. This is called the Very Large Array, and the complete name is Carl G. Jansky. So Carl G. Jansky is a scientist. He's called the father of radio astronomy. So radio astronomy, that is another branch of astrophysics or astronomy, where scientists are studying space or astrophysical phenomena using radio waves. So or using radio telescope. That is there. That branch is called a radio astronomy. Okay. And you can see the VLA, very large array, is actually comprised of 28. Okay, there are 28 telescope of 25 meter radius. Okay, so you can see that each of them, okay, 1, 2, 3. If you count it, it's actually some 28 of them are there. Okay, 28 of them, and each of them has a size of 25 meter. Okay, the size of the dish is 25 meter. And you can see it is actually spaced in a Y-shaped array, something like this. Okay. Something like this place, something like this. Okay, 28 of them. I'm not counting it properly, just giving a glimpse, something like this. So that effectively it becomes something this big and deployed in a Y-shaped array of 21 kilometer. Okay, so it is total area of coverage is actually something around, it spans around 21 kilometer actually. Okay, it built during 1973 and 1980. So 25 meter for a single dish. Okay, so this is Carl Jansky is the father of radio astronomy, and usually the energy of a radio wave sometimes represented in a unit called a Jansky. Okay, there is a unit, something like we say that energy, something like a joule or something. There is a specific unit called a Jansky is there. Okay, that's also named after Carl G. Jansky. He's called the father of radio astronomy. So this is about the very large array. So before this is about the radio, and this is about the okay. And now, as you know, the radio telescope are actually always on the ground because, as you know, it is actually almost all the radio waves are actually being received on the Earth's surface. So there is no need to go above the atmosphere. But there are other telescopes, something like Hubble Space Telescopes, or many other telescopes are actually orbiting around Earth. Okay, and the most famous telescope is actually Hubble Space Telescope, and actually we can have a 2-hour session especially dedicated to Hubble Space Telescope, the mechanics, and not about the instrumentation or the technology, just the discoveries that happen from Hubble Space Telescopes actually take maybe 1 or 2 days is not enough to discuss them in detail actually. Okay, so anyway, I'm not going to that. We have to just need to know Hubble Space Telescope. It is also still working, and the Hubble Space Telescope launched in 1990 by NASA. That is even before I'm being born. Okay, it is older than me actually. Uh, and orbits Earth and has provided stunning images and valuable data. It has deepened our understanding of universe, age, expansion. Hubble's images of galaxies, nebulae, and planets have captured the public's imagination. As you know, you might have been seen these pictures. Many of the wallpapers are available, so Hubble is that popular. Okay, and the interesting thing about Hubble Space Telescope, it is actually a serviceable telescope, okay, or repairable telescope. Usually, it is actually upgradable. Okay, so something like you receive the software update in your phone instead of that, or something like if you have a laptop or a PC, then what we do is that the RAM is not enough, so that I will go and buy a new RAM, or if I need a hard disk, I will upgrade my hard disk. Similarly, this telescope is also made to be upgraded. Okay, so someone can go there and repair it. So that is actually lucky we made it like that, because that I will explain later. And this is the April 24, 1990, and space shuttle. It is actually launched by Space Shuttle Discovery. So if you know that 90s, 19, maybe up to some 2000, yeah, 2004 or something, it was the era of space shuttles. Okay, and it is actually launched by Space Shuttle Discovery and deployed on 1990. Entered service May 20. So this is a service. Okay, so it will decay. Decay means there are some energy sources for this telescope there. So that will be decayed in 2030 to 40, or other, if nothing happened, it can last up to 2030 for sure. And it is a Ritchie-Chrétien reflector telescope. See, reflectant. Ritchie-Chrétien is a similar design, something like, it's usually called as RC telescope. It is something similar to that of the Cassegrain. It is not exactly the Cassegrain, but that idea is. Now you can see the mirror size is actually 2.4 meter. Okay. It is even taller than a full-grown man actually. So it is 2.4 meter, and just leave the focal ratio and collecting it. Okay, and see, it can completely see the visible light and near infrared and ultraviolet. What do you mean by near infrared? Yeah. So when you take that, if you take, this is the visible light. Okay, visible. Okay, then here is infrared. So the complete infrared is something so big, infrared. So there is some part of infrared that is called the near infrared. That near infrared is actually visible for Hubble Space Telescope. And there is something called a far infrared that is here, which is not observable by HST. But anyway, all other ultraviolet and near infrared is actually observable. So we can say that it is actually observing 3 different kind of lights. Okay. So that is Hubble Space Telescope. But it is such an important mission that it has had a problem actually. So when they send the telescope, this is an initial image. You can see that. Okay, why this is the camera called a WFPC. That means wide field planetary camera. So the first image it got is something like this. Even if you don't feel initially that is a good one. It's not a bad one, but it's actually a blurred image. So the blurring is actually happened because you can see within the weeks of launch of the telescope, the returned images indicated a serious problem with the optical system. Images of point source spread out. So point source means something pointy should look pointy in the telescope as well. So something happened, or that point sources become something kind of a blurred one. Then the primary mirror had been polished to the wrong shape. Okay, this is why I mentioned yesterday, making this mirror is not a silly task. Okay, it is so serious business. Okay, although it was believed to be one of the most precise, see, it is most precisely figured optical mirrors ever made. okay, smooth to about 10 nanometer. Okay, so nanometer is a so tiny size actually. So anyway, it is so finely made, and it is said that it is something like we say about Titanic, it won't ever sink, something like that. So it is also optical mirror so fine, but the problem is that there had a small problem with the polishing. There is a tiny error in the polishing at one part of the mirror. Okay, so that happens, so that mission is completely actually useless. It become, but as I mentioned, it is actually a serviceable telescope. Okay, uh, so for that they actually added a servicing mission, something like we can call it as, usually if you use a specs, okay, some spectacle for your eye, then actually if you remove it you will see a blurred image, and if you place in front of your eye you get a sharp. Similar kind of a spectacle is actually a correcting spherical correcting mechanism is actually uh, placed for this Hubble Space Telescope. Okay, that happened on, I don't remember the exact date actually. So anyway, that correcting optics is called, the name of that is Corrective Optics Space Telescope Axial Replacement, or it is called shortly called COSTAR system, was designed to correct the spherical aberration or the problem with the polishing and for the light to get focused. Okay, and that service mission one flew aboard Endeavour. Endeavour is another space shuttle. Actually, they will go in the space shuttle and it will actually flew parallel to or too near to the space telescope at the same speed at that of the space telescope, and it can actually grab the space telescope. Just go to YouTube, and maybe in YouTube there will be videos actually. And there is a famous IMAX movie, okay, an IMAX, it is not a film actually, an IMAX documentary based on the repair of the last service mission of uh, the last servicing happened in, yeah, somewhere in 2000 something. Okay, so in 2000 a servicing mission happened, and IMAX, that entire servicing mission had been shot in IMAX, and actually there is an interesting uh, documentary regarding that. Okay, so just try to get and watch this. And in January 13, 1994, NASA declared the mission a complete success and showed their first sharper images. See, this is the difference. Okay, so this is the first image that it took, and this is after correcting. Okay, so this is something like huge difference that you can see. So anyway, this top figure is the mirror being polished. Now see the size of that mirror compared with a person standing there. Okay. Then Hubble's important discoveries, just important one, age and expansion of the universe. The estimated age of universe is actually accurately been able to uh, be calculated after Hubble. So it was something around, we know the range something between 10 to 20 billion years. It was a rough one. Now we know that it is almost certainly with some minor error, it is around 13.7 billion years. So that is after Hubble it happened. That high resolution spectra and images provided by HST have been especially well studied to establish the prevalence of a black hole. It is not an image of a black hole, but by studying some other images, it was able to calculate, or it was able to speculate that the black hole should exist. Okay, and uh, some other things. Actually, it is predicted a reappearance of supernova, and it is actually first ever it could capture by Hubble on December 2015. In March 2019, observation from Hubble data from the European Space Agency's Gaia Space Observatory. So there is another space observatory called Gaia. Okay, so Gaia is another space telescope which is actually accurately measuring the distance. Okay, or basically something called a parallax. Okay, of different stars in our own galaxy. So by measuring from that parallax, actually we can get the exact position of these stars in our galaxy. So by getting the positions of the stars and by measuring its mass indirectly using, or by estimating the mass using Hubble Space Telescope, we are actually able to calculate the uh, mass of our Milky Way galaxy, and it is found to be 1.5 trillion times that of the mass of Sun. Okay, so that is also, these are only a couple of discoveries by important discoveries by HST. So another interesting thing, as you know, if you look deeper and deeper to the universe, you can see the past. That is something that we know. Okay, so ground-based observatories till 1990 were actually able to see this far. Okay, something 6 billion years after Big Bang. Okay, this is the deepest thing. So from this is the past we were able to go. That means some billion years after Big Bang. Now, in 1995, Hubble Deep Field, that's an interesting image. We are able to go up to here. Hubble Ultra Deep Field could go here, and Hubble Ultra Deep Field IR could go here. And this is not future right now. Okay, this is an old diagram. That is why it is written future. JWST can even go just after it is able to observe the universe as if it is just after 200 million years, just after the Big Bang. Okay, so that is why one reason that we are making bigger and bigger telescope. And by the way, this is the Hubble Deep Field, this is Hubble Ultra Deep Field and all. Okay, so now that successor of, maybe usually it's called the successor of Hubble, that is the James Webb Space Telescope, that is the JWST in short. Okay, so here you can see here, this is a segmented mirror, as you see. Okay, so it is 6.5 meter diameter. See, the Hubble was something around 2.4. Okay, yeah, Hubble was 2.4. It is almost three, not exactly three times, it is almost 2 to 3 times larger than that of Hubble. Okay, and it is a segmented mirror made of gold plated beryllium. Okay, so gold plated beryllium is used because it can reflect infrared. Okay, so the design is also something similar to that of a what we explained yesterday, that is a Cassegrain design. Something like the light will come here and it will be reflected and will be received here. So here, instead of going to the back, maybe to the back side it will go, and there will be some other instruments as well. So it is also a similar design. Okay. So it is launched in 25 December 2021. So hopefully you may learn about it. And it is actually not orbiting around Earth. That is another. Hubble is actually, if this is Earth, Hubble is actually orbiting around Earth, like a satellite. Like it's a satellite basically. But the case of JWST is not revolving around Earth. Instead of that, it is actually orbiting at a point called L2. Okay, so assume that this is the Sun and this is the Earth. Okay, so when Earth is orbiting around the Sun, there are some points called the Lagrange's point. Okay, maybe written here, may not be. So it is in the Lagrangian points. Lagrangian points. Okay, there are 5 Lagrangian points are there: L1, L2, L3, L4, and L5. So these points are called equilibrium points. Okay, so the idea is that around that equilibrium point, actually we can orbit telescopes or orbit things. Okay, so it will act like an attracting point. So for a satellite to be orbiting around something, there should be something to attract. So for that, instead of having something, we can even use that L1, L2 points, so around which that L2 is actually orbiting. So around L2, this satellite is orbiting. One advantage is that it is not near to Earth, so it can avoid a lot of infrared, so that it can properly observe the universe in infrared without being affected by the Earth's infrared radiation. So that is called a JWST. So this is a comparison of this image is called pillars of creation. It is being compared with the left one is taken by HST and the right one is taken by the JWST. Okay. So it is planned for 10 years, and that means it is 2022. That means 2032 maybe, and it may also extend its life. So expected lifetime is actually 20 years. Diameter is this. Okay. Okay, then Kepler Space Telescope. This is another interesting I have added because it does something else. Kepler Space Telescope, named after Johannes Kepler, as you know, and it announced its retirement in 2018. Okay. Anyway, this telescope has a specialty. It is dedicated to look for something called exoplanets. Okay. So the purpose of exoplanets, or the exoplanets, are planets which are orbiting around other stars. Okay, so we know our solar system where the planets are orbiting around the sun, but there are another planetary systems in which the planets are being orbited around other stars. So to detect them, there is a method called a transit method. So transit method, imagine that there is a sun, okay, there is a star. Okay, this is a star. We cannot actually see them, but when we can see the star, but we cannot see the planets. But when the planets goes in front of that, okay, when it is crossing, the light coming from the star get a dim, okay, a dip. Okay, by analyzing this dip, actually we can detect the presence of a planet. Okay, so that is called the transit method. Okay, it is the transit method of exoplanet detection. So Kepler is a space telescope which is actually observing for transit methods or transit, and is dedicated for that. And as of August 2022 to 56, so this is just some 2 years back actually. So you have to search for the current date. Current data is even more than, I think it is almost some 3,000 or 4,000 exoplanets been already detected actually. So that is about the Kepler space telescope. So these are on, there are many other. Spitzer is there, and many other telescopes are there. Actually, Gaia mission is there. So there are many different space telescopes are there. So Parker Solar Probe is there. So many other things are there. SOHO is there. So I'm not going to mention all of them because it will take more time. Now let me discuss about, oh, it's already 6:30, but I will go through these slides as well, and the remaining will be discussed tomorrow, don't worry. Anyway, we will complete it promptly. So gravitational wave ups. So whatever we were discussing till now, it is something like what is called a light, or simply electromagnetic spectrum. So that we discussed. Other than this light, there are some other things that is actually coming from the space. Okay, one such example is actually the gravitational waves. Okay, so gravitational waves are actually something like we can imagine, or Einstein, by Einstein actually, there is something called a space time. Okay, space time can be imagined under something like a fabric. Okay, you can, this picture has a problem, that is it is two-dimensional, or the fabric of cosmos is something looks like a plain some cloth or something. That is the only way we can imagine. Okay, so imagine it like this. So through this fabric of cosmos, okay, when something is moving, okay, it will make ripples. Okay, it is, you can imagine it something like in some water, two fish are, imagine two fishes and they are orbiting each other, they are something like dancing together, then it will make some ripples. So those ripples can be detected in Earth. But for Earth Moon system or anything, even if you dance, it is actually making these ripples, but it is so feeble we cannot actually detect. But when two black holes or maybe some neutron stars are revolving around like this, so they are so massive and dense, so this ripples become significant and we can detect them. So this waves that is made by any massive object that is moving or accelerating, then they are called, that ripples in the fabric of cosmos or the ripples in the space-time is called the gravitational waves. Okay, these are the waves in gravity, or not in gravity, sorry. These are the ripples in the space-time. So that is what we receive at here, and it can be we can actually detect them on Earth, and those observatories are called gravitational wave observatory. But I am not going to explain how it works anyway, because it needs some other knowledge of interferometry and all things. But I will include that in the slides. But don't worry. But anyway, you can use it in the future. So one such in gravitational wave observatory is LIGO, Laser Interferometer Gravitational Wave Observatory, or together usually in short it is called LIGO. Okay, and it is actually comprising of two sites. Okay, it is not just one observatory, it is actually two sites. Okay, in United States, one is in Livingston and another one is Louisiana. You can see some L-shaped pipes will be there. So this is Livingston and this is Stan. Okay, and it can actually detect the gravitational waves. Okay, And this is another one. After this one, there is another one is coming, that is called the LIGO or advanced LIGO. So this is another one, Virgo interferometer, and this is also gravitational wave observatory. Now we have to discuss about neutron observatory and something like the cosmic ray observatory. So that we will discuss tomorrow, and we will maybe some time will be taken at the starting of tomorrow. Then we will discuss it.